Good morning or good afternoon to those joining us from Mexico and the UK. It's a pleasure to welcome you to another session of our UNAM-UK Student Seminar Series, an initiative that's designed to highlight Mexican students' academic and scientific work in Mexico and abroad. We are delighted to have you join us in this online space where we continue to foster connection between academic communities from international, interdisciplinary, and collaborative perspectives. To begin today's session, I am pleased to introduce Farid Bustos, President of the Mexican Society of Students in the UK, MECSOC, who will be the moderator of this seminar. Farid, please.
Yeah, thank you very much, Dr. Del Rio. It is a pleasure to be here today and collaborate with the UNAM-UK Center in hosting this session. We're honored to welcome Georgina Marisol Molina Granados, who will be presenting the talk entitled LIBS Application and Its Potential, where she will explore the features, benefits, and current challenges of laser-induced breakdown spectroscopy, or LIBS. This event is being streamed live on YouTube. We invite you to send in your questions throughout the session. We will dedicate time at the end of the talk to address as many of them as possible. We're also pleased to include a brief intervention by Mr. Nicolas Camposano, which is one of the Georgina social service students who has been working closely with her, and we're very glad to share their voice today as well. Before we begin, allow me to briefly introduce our guest speaker. Georgina Marisol Molina Granados is a lecturer in physics at the Faculty of Sciences in UNAM. She's currently pursuing a PhD in Earth Sciences at UNAM's postgraduate program and has taken part in prominent international conferences in spectroscopy, including the Colloquium Spectroscopicum Internationale and the first Latin American LIBS held in Mexico City. She also coordinates two social service programs, one in physics and another one in biology. We're truly grateful for her time and generosity in sharing her work with us today. And with that, I will now hand over the session to Georgina.
Thank you, Farid. Well, good afternoon, everyone. Thank you so much for being here. Let me share the presentation. Okay. Before diving into the main topic of this talk, LIBS and LIBS application and its potential, I like to take a few minutes to talk about where we come from, the environment in which we do our research, and why the context matters. We often think of science as something universal and detached from place, but in reality, we are where and how we do research shapes the kind of questions we ask, the problems we prioritize, and the solutions we envision. I believe that understanding our background can open doors for collaboration and mutual growth. So let's begin by looking at where we come from. Let me introduce our institution. I work at the National Autonomous University of Mexico, or UNAM. It's not just the largest and one of the most prestigious universities in Latin America, with over 360,000 students. It's also one of the oldest, founded in 1551 under the name Real y Pontificia Universidad de México. Today, UNAM plays a critical role in shaping science, culture, and education in Mexico and throughout Latin America. Its main campus Ciudad Universitaria, or CEU, is located in the southern part of Mexico City. In 2007, CEU was declared a UNESCO World Heritage Site, not only for his striking architecture and iconic murals, but because it embodies a unique vision, a modern university that integrates knowledge, art, and community. Some of you may have heard of Diego Rivera, David Alfaro Siqueiros, or Juan O'Gorman, famous muralists whose work decorates our campus, telling the story of Mexico's struggles, dreams, and ambitions. Beyond its beauty, CEU is home to an incredible, vibrant academic and research ecosystem. At UNAM, thousands of researchers are working across disciplines to address both local and global challenges, from climate change and public health to space exploration and artificial intelligence. UNAM is a powerhouse of scientific discovery. Within UNAM, I'm part of the Institute of Applied Sciences and Technology, ICAT. ICAT is a multidisciplinary research center that brings together physicists, engineers, and material science with a shared mission to bridge the gap between fundamental science and real-world applications. This applied spirit is at the heart of everything we do. Our projects range from developing new sensors for environmental monitoring to designing advanced materials for aerospace and or biomedical applications. At ICAT, I work in the Laboratory of Fotofísica, directed by Dr. Mayo Villagran. Our lab focuses on laser-based techniques for material analysis, and our research spans both fundamental studies, like how light interacts with matter, and technological development, like building instruments for industry or field use. Among our main research lines, one stands out for its versatility and growing relevance: LIBS, laser-induced breakdown spectroscopy. This is the technique I'll focus on for the rest of the talk. What is LIBS? LIBS is a type of atomic emission spectroscopy that uses a high light energy laser pulse to ablate, that is to remove, a tiny amount of material from a sample. This process forms a luminous plasma, and the light emitted from this plasma contains the spectral fingerprint of the elements within the sample. Imagine it like this. The laser acts almost like a very tiny controlled lightning bolt hitting the sample. The energy is so intense that it tears atoms apart, and as the plasma cools, the atoms recombine and emit light at a specific wavelengths unique to each element. The basic setup of LIBS includes a pulse laser, often a Q-switch neodymium jack, optics to focus the beam, a spectrometer and detector to collect the light, and a computer for data processing. The entire process happened in just microseconds, and analyze can begin almost immediately. This speed is one of LIBS' most attractive features. How does it work? Let's walk through the steps. First, the laser pulse strikes the surface, creating an extremely high temperature spot, tens of thousands of degrees Kelvin. Second, the material at the surface vaporizes, forming a microplasma made of ions, atoms, and electrons. As the plasma expands and cools, atom emissions light at characteristic wavelengths. Or, a spectrometer analyzes this emitted light to produce a spectrum. By comparing the spectrum to known reference data, we can identify which elements are present. This technique is remarkably flexible. It works on solids like metals, rocks, and polymers, powders like soil or pigments, liquids with special setups, and aerosols, tiny particles suspended in air. Unlike many other analytical methods, LIBS doesn't necessarily require a vacuum, extensive sample prep, or even physical contact. Why is LIBS valuable? Because LIBS offers several critical advantages. Speed. Analysis can happen in real time and results can be obtained in seconds, important for field work or rapid decision making. Minimal sample preparation, often just point and shout. In most cases, samples can be analyzed directly. Microscopic destruction. Only a microscopic amount of material is ablated. It is usually measured in micrograms. Versatility. Suitable for metal, soils, biological tissues, archaeological artifacts, and more. Remote sensing. LIBS systems can operate several meters away, useful in hazardous and inaccessibility environments. Broad element range. It can detect light elements like hydrogen or lithium, and heavy elements like lead or uranium. It's also possible to create 2D or even 3D compositional maps of a sample surface using scanning techniques. For example, imagine analyzing a heavy metal contaminated site. With LIBS, you could walk around with a portable device and map the contamination on site, rather than taking dozens of soil samples back to the lab. Now, let me give you a few examples to illustrate how LIBS is being used in real-world applications. Space exploration. NASA's Curiosity and Perseverance rovers on Mars are equipped with a LIBS system called ChemCam. Each laser shot provides information about Martian geology without needing to drill or dig. Cultural heritage. Conservators use LIBS to analyze delicate painting, statues, and manuscripts without removing samples, preserving artifacts for future generations. Environmental monitoring. Detecting pollutants like lead, mercury, or arsenic in soils or water bodies. Industry. In metallurgy, LIBS is just for real-time quality control. For example, checking if an alloy composition is correct during steel manufacturing. Agriculture. Researchers have applied LIBS to assess soil nutrients quickly to optimize fertilizer use, promoting sustainable farming practices. Despite its many strengths, LIBS face challenges, which opens the doors for interesting research. Quantification. While LIBS is excellent for detecting what elements are present, quantifying their exact concentration can be tricky. Accurate concentration measurements are complicated by factors like matrix effects and plasma variability. Researchers are working on better calibration methods, including multivariate analysis and internal standards. Signal enhancement. Techniques like dual pulse LIBS, where a second laser pulse re-excites the plasma, can significantly improve sensibility. Machine learning. AI and machine learning are now essential for processing complex LIBS spectra, identifying subtle patterns, and making fast, reliable classifications. Portability. Compact, rugged LIBS systems are crucial for field work, from mining sites to disaster zones. Hybrid techniques. Combining LIBS with Raman spectroscopy or mass spectroscopy can provide both elemental and molecular information from a sample. Because LIBS touch so many fields, physics, chemistry, engineering, computer science, it's a natural platform for interdisciplinary collaboration. Physics can study plasma formation, optics, laser. Chemistry can focus on elemental identification and matrix effects. Engineers can do instrumentation or robotics, and computer science can improve signal processing and machine learning. Possible projects include building a portable LIBS device for rapid soil testing in agriculture, developing machine learning models for spectral analysis, or creating environmental monitoring stations for urban pollution. There is a lot of space for student involvement too, from instrumentation design to data analysis, outreach, and field work. To summarize, LIBS is a flexible and fast elemental analysis technique with a wide range of applications. It has both scientific and practical relevance. It continues to evolve, offering opportunities for innovation and discovery. And most importantly, it invites collaboration. I'm very interested in forming partnerships with colleagues and students who want to explore LIBS in their own research. Whether you are working in analytical chemistry, environmental science, cultural heritage, or data science, I believe there is a place for LIBS in your work. We could explore joint publications, outreach programs, or even grant proposals to bring together our expertise. Now, I would like to present a specific example of research in the field of LIBS, focusing on the phenomenon of self-reversal of emission lines. This study represents an important step toward a deeper understanding of plasma behavior and spectral interpretation in LIBS diagnostics. It has already been completed and submitted for publication as a scientific article. After this, there will be a second example covering other lines of research carried out in the photophysics laboratory, which will be presented by one of our students. But first, I will focus on the LIBS example. This scientific article name is Characterization of the Cell Reversal Phenomenon of Silver Resonant Lines in Laser-Induced Breakdown Spectroscopy Experiments. In this study, we investigate the phenomenon of self-reversal of spectral lines in LIBS spectra by analyzing the temporal evolution of self-reverse emission lines from both neutral and ionized silver, using different laser energies and lengths to target distance. Why we study self-reverse? In LIBS experiments, resonant transitions, or those involving very lower energy levels, can exhibit a dip at the center of the emission line, a phenomenon known as self-reversal. This effect arises from the reabsorption of radiation emitted from the hot central plasma by cooler atoms located at the plasma's periphery. Unlike self-absorption, which occurs to some extent in all emitted sources, self-reversal only appears in non-homogeneous plasmas, such as those produced by laser pulse, where the electron temperatures and number density are higher at the center than at the edges. Because of this, self-reversal has been studied extensively as an indicator of plasma inhomogeneity and to mitigate its influence on LIBS measures. The dependence of self-reversals on factors such as target material, laser energy, wavelength, focusing conditions, ambient pressure, and surrounding medium highlights its complexity. Existing models typically describe the laser-induced plasma as consist of two regions: a hot, dense core and a cooler, less dense periphery, both assumed to be a local thermodynamic equilibrium, although more intricate models are also considered. In our work, the observation of strongly self-reversed lines from both neutral and ionized species suggests that the outer layers of the plasma are optically thick. Our results also indicate that the electron density at the plasma's periphery can be significantly lower than at the center, raising doubts about the validity of local thermodynamic equilibrium conditions throughout the plasma. Experimental evidence supports the idea that the cold atoms responsible for self-reversal resides at the plasma edges, beyond the shock wave generated during plasma formation, particularly in the regions of low pressure. Therefore, not only are a temperature and electron density gradient within the plasma necessary for cell reversals to occur, but also the presence of a shock wave, which create a low pressure zone where a large population of atoms and ions responsible for cell reversal can persist over time. Additionally, the simultaneous observation of silver 1 and 2 emissions over an extended period points to a relatively low electron density, likely insufficient to fully maintain local thermodynamic equilibrium conditions. To close, I like to emphasize that LIBS is not just a tool, it's an opportunity to rethink how we analyze materials, to collaborate across disciplines, and to solve problems that matter to our society. LIBS has so much potential, and I believe that together we can push its boundaries even further. Our door is always open to new ideas, questions, and projects. Now, I'd like to introduce Nicolas, an undergraduate student who recently completed his social service in our lab. He worked on another key line of research in our laboratory, random dye lasers. He will spend the next minutes sharing his experience, what he works on, and what he learned.
Thank you. Do you hear me? Do you see the presentation? Or can you see it?
Yes, Nicolas.
All right, great. Hey, I'm Nicolas Capsano. I am finishing my social service at ICAT. I had the pleasure of working with Georgina and learning about LIBS and seeing all of its applications. And afterwards, I proposed, after talking to Dr. Mayo Villagran, about random blood laser, of using or seeking to find different fluorescent compounds for the implementation of dye lasers. Mainly, all right, so our main objectives were to extract the fluorescent compounds from Mexican kidney wood, which is Eisenhardia polystecha, measure the absorbance, fluorescence, and excitation spectra for these extracts, determine if they are viable for dye lasers, implement, should it be viable, a laser, and as a secondary objective, I had the objective of producing material for investigation at ICAT using recycled and low-cost materials, focusing on the necessary parts for a dye laser. So I wanted to, for example, we used hard drives to make mirrors and DVDs to make partially reflective mirrors, and we tested these in a laser cavity that worked, and it actually worked. So yeah, well, it's kind of a spoiler, but whatever. Mexican kidney wood is a tree native to North America. It extends all the way from Mexico to Canada. Its main fluorescent compounds are matlaline and coatline 1 and 2. And matlaline is actually one of the, if not the oldest fluorescent compound that's been discovered. So what did we do? We extracted these compounds from a powdered version of the tree, which we obtained from El Jardín Botánico at UNAM. And we macerated this powder using 5 solvents: water, isopropanol, ethanol, methanol, and acetone. We actually here didn't really know if this, well, you can see in the picture that we have different colors of fluorescence. For example, number 1, which is in the middle, is blue, which is water. Fluorescence of these compounds under UV light in water is blue, but if number 5, which is on the far left, is actually yellow, that's what you get when you have the compound extracted with acetone. We didn't really know what this was about, so we did some thin layer chromatography plates. Here's a picture of how that looks, and this is one of the results. The order of these is from bottom to top. In the picture on top, it's water, isopropanol, ethanol, methanol, and acetone. So here, what do we see? We see that we have compounds that fluoresce blue and have a very high retardation factor, and we have some fluorescent compounds that fluoresce green. And these show in very separate, well, not so separate, but distinct bands. So that suggests that there are different compounds present in the kidney wood that have fluorescent abilities, and they can be separated using chromatography. Afterwards, what we did was characterize these extracts. Here you can see the absorbance spectra. These are significantly different from what we expected given the literature, and we attribute that to the fact that we probably extracted a lot of different compounds aside from those of interest. And that's what this graph is reflecting for us. On the right, you can see the visible appearance of these extracts in water, ethanol, and acetone. As you can see, in water, it's actually very dark. In acetone, it's almost completely clear. And we can tell that in acetone, which is the green line here, there's almost no absorbance in the visible spectrum. But there is significant absorbance in the UV, although that can't be characterized so well because acetone absorbs well in this range as well. So we continue to see the emission spectra, which are also very interesting. For example, we already saw that if we have the extract in water under UV light, we see blue fluorescence around 470 and around 470 nanometers. And well, if we excite with 505 nanometers, we can also see fluorescence at around 530 nanometers. So the emission spectra is actually quite wide. For example, in methanol is one of the most versatile solvents we found because the emission spectra is actually incredibly rich, depending on what you use to excite. I omitted a lot of data from these for you to be able to see what's going on. So this is the emission spectra for the solvent methanol with our kidney wood. And we can tell that it's got an emission peak at around 520 nanometers. And we can excite it with 380, 412. We'll see that further. I'll just go by this. This is isopropanol. These bands are actually very similar to methanol, but not to water. All right, this is the excitation spectra. We use these were actually our main tool because we thought that absorbance spectra was going to be the key, but given how we had so many contaminants in the sample, it wasn't. And in this case, the excitation spectra was great because it told us exactly where our maximum are for excitation. And well, we know that if we hit our sample with this wavelength of light, it will fluoresce the hardest we can get it to. For example, we have two different graphs here. The first one is for fluorescence, the dots for fluorescence at 466 nanometers. We see that we have a range around 420 to 430 nanometers to excite. And in the line graph is for fluorescence at 532, so like greenish. And we see there that if we excite at around 500 nanometers, we would get the most light out of it. Okay, so then after doing all of this, we implemented a laser with mirrors. This is a picture of how the montage is. So you have an excitation source coming from below that is expanded into a line using a cylindrical lens. That line is focused onto a quartz cuvette that contains our dye. And that quartz cuvette is sandwiched between two mirrors, one that is fully reflective and one that is partially reflective. And these mirrors, we want them to be as parallel to each other as they can, and as parallel to the line that we are focusing on the cuvette. All right, but there was an issue here. The lasers that they have available at ICAT, that they had working at ICAT, the wavelengths don't align with what we're seeing at the excitation spectra. So we had to work on getting this machine working. This is a wonderful machine, incredible, it's a dream. It's a laser that can emit light all within the visible spectra, and it can actually emit light into the deep UV. It does this using a nonlinear optical crystal. Here's some pictures of it in operation. And you can tell that what's going on here is that the laser is, the crystal is rotating, and the angle that it is at determines the color that we're seeing. So we can see from purple all the way to red, we have emission. And why we did this is that we needed to be able to excite at 400 and something nanometers instead of 355 or 532 nanometers, or infrared, which are the three we had available. All right, after doing this, what we had to do was determine which concentration and pH were optimal for our dye. And we did this using photography. That was kind of the most reliable way we found, which you can see some of the photos here, not all of them. And yeah, we found that a concentration of 0.0007 grams in 4 milliliters of water was the most effective at fluorescing, and the pHs that were the most fluorescent were around 11. Yeah. Okay, so having done that, we actually couldn't be able to get it to lace. we put everything in the cavity. We used rhodamine and fluorescein to check if the cavity was working as intended, and it was, but the dyes just weren't fluorescing. So that's when we kind of tried whatever, and we kind of have some conjectures about what worked. We used Alconox, which is a detergent, accidentally, and that kind of seemed to do the trick. So I'll just go on to the results. All right, after we found the fluorescent, the lacing solution, and well, I mean, it wasn't just the Alconox. We used a mix of 50% methanol and 50% isopropanol as solvents instead of just only the alcohols, and that might also be the reason why. All right, here you can see the spectrum. The blue line is the spectrum of the laser using kidney wood. The turquoise line would be for the rhodamine laser, and the green line would be for the fluorescein laser. Well, we had another conjecture that what could be the factor for inducing lacing would be the pH. So we controlled the pH in an ethanol sample using caustic soda, getting it to a pH of 11, which was the same as all the other samples we had. And you can see that it's not lacing. All right, and so I measured the half measure, or yeah, anchura a media altura of these lasers. And for the kidney wood laser, is actually really close to the rhodamine laser, between 6 to 10 nanometers. So that's really good, and you can tell that the signal is quite intense, actually more intense than the fluorescein and the rhodamine. So what did we find during this time? Well, we found that Mexican kidney wood is a good source for fluorescent compounds that are able to be laced given certain conditions. This is also useful because it exhibits strong fluorescence, solvatochromism. What is that? What we talked about, the fact that the fluorescence is a different color depending on which solvent it is in, and we actually checked if this was reversible, and given what the evidence we have, it seems to be. What do I mean by that? I have a sample, I dissolve it in water, it fluoresces. I dry it and put it in ethanol or acetone, it might fluoresce yellow, and then I dry it and I go back to water, it would fluoresce blue. It is also a good measure of pH, given that its fluorescence will be quenched at lower pH and will be intensified up to a point at higher pH. Yeah. Well, we found that either Alconox or a measure of isopropanol and methanol are the keys to making these lasers work, and that it is possible to pump it in a range from around 410 to 400, no, actually from 400 to 420 nanometers in water. There's actually a lot of work that is open, like that could be done just from using different solvents, from trying to find, well, we actually achieved finding a dye that works, that isn't impossible to align, that isn't extremely toxic for a dye laser. That's great. And we wanted to find a candidate that could work in a random laser. But given the nature of what we found is necessary to make these lasers, it's still not biologically compatible. So that's also an open line of investigation, I guess. Yeah. And well, this is a pre-picture of kidney wood. You can tell that there's a distribution of the fluorescent compounds that is interesting. The green is mostly in the center, and the blue fluorescent compounds are mostly outside. Yeah. So that's it. Yeah.
Thank you, Nicolas. And if you are curious, if you see a connection with your work, or even if you just want to learn more, please don't hesitate to contact us. We love to hear your questions and explore possibilities with you. So thank you again for your time and attention.
Okay. Thank you very much, Georgina, for this really interesting talk webinar. We've got a couple of questions from Luis. The first one is he asked that when you were doing the measurements of the ovulation spectrum, what was the physical process where you could identify the compounds of the material? Would that be an optical process such as electronic transition, or a mechanical process such as Raman, or any other type of process?
Yeah, I guess it's an optical process. This question is in Spanish, so if I can answer in Spanish. Yes,
yeah.
Sí, es que LIBS es una espectroscopía de emisión atómica. Entonces, las espectroscopías de emisión atómica utilizan pues un proceso óptico. En este caso, la luz que emite el plasma es la que tiene la información de la muestra, y donde se recolecta entonces o se resuelven en las diferentes longitudes de onda, pues para después en el espectrómetro ya ver la identificación de las líneas espectrales correspondientes a cada elemento, ¿no?
Ok, pues una segunda pregunta que también hizo Luis es respecto a la fluorescencia de estos compuestos orgánicos. En este caso sería el tinte. ¿Cuánto tiempo mantienen la fluorescencia? O si esta fluorescencia es a través de procesos electrónicos.
Esa no sé si la quieres contestar tú, Nicolás.
Con gusto. Bueno, la pregunta la interpreto de dos formas. Por cuanto cuando nosotros estamos golpeando, en español o inglés, bueno, está en español. Cuando nosotros estamos golpeando con el láser, puede ser que estemos destruyendo la molécula, y eso, pues los tintes se van ablancando, se van destruyendo y se van desapareciendo. Bueno, eso dependiendo de la intensidad, pues bastante poco tiempo. O si le pegamos con un poco de menos intensidad, en realidad es una molécula bastante resiliente. La otra interpretación que se me ocurre es si te refieres al tiempo de fluorescencia, y eso es más o menos como 4 nanómetros. Está un poquito más allá del umbral de lo que pueden medir las máquinas en el CAD, pero es información que se puede determinar de las gráficas que ya tenemos con el láser. Entonces, eso es cosas que podrías quedarte pendiente para después. Sí, gracias.
Muchas gracias. Another question. Could you explain how you can consider the plasma in the thermodynamic equilibrium? Is it heating and then cooling?
Thank you. The equilibrium is just about some microseconds, and there are some measurements that we consider to set that plasma is in local thermodynamic equilibrium. Such measures are like the temperature of the plasma and the number of density. And there are so many different forms to obtain these measures, and with some results that we just know previously, we can compare the measurements, and that's how we can consider that the plasma is in thermodynamic equilibrium.
Thank you. There's another question. Could you tell me any differences between the LIBS and the synchrotron studies?
Can you repeat the question again, please?
Yeah, they're asking if you could or tell us or what are the differences between the LIBS and the synchrotron studies?
Synchrotron. I just don't have deep in the synchrotrons and how the measures are, but maybe there are just some difference, but you can email us that I can read more about the topic of synchrotron. It's more easy for me to answer that question, no? But LIBS, like I said, is about see the compounds of the plasma, of the sample plasma, by a different physical process like ablation. Ablation means a lot of processes that are that are in the sample, like vaporize, like like difference in temperature, like recombination of ions. So there are a lot of physical process taking in the sample place.
Okay, thank you. Now, this is a question I've got. If I were to use LIBS, could I tandem the LIBS analysis with any other spectroscopic measurements, such as Raman, as you said, to identify the molecular structure and then kind of identify the say like the with Raman I could identify, I guess, the bonds, the functional groups, and then with the LIBS I could further identify the structure probably.
Yes, with a combination of the two techniques is when the most potential you can have, because Raman gives information of the bonds of the component, and LIBS gives you the elements that are present. So with that two measurements, you can have a more big picture of your process or the compounds of a sample that you're analyzing, or anything is you can imagine. You know? It's like the Martian rovers that we said of the NASA's rovers. They have many techniques. Some of them are Raman and LIBS, and with that they are having a complex analysis of the Martian rocks and soils.
Okay, otra pregunta que está haciendo el profesor Antonio Río. ¿crees o consideras que el LIBS podría aplicarse en conservación del patrimonio cultural o de artefactos arqueológicos?
Sí, completamente. De hecho, ya hay algunas áreas o líneas de investigación en patrimonio, porque el LIBS da la ventaja de que como es mínimamente destructivo, pues ayuda mucho a la conservación, porque muchas otras técnicas necesitan pues remover una gran parte del artefacto, de la pintura, de lo que sea, y entonces pues se pierde un poco de ese patrimonio, ¿no? Entonces con LIBS, como es micro, lo que se usa, es muy fácil que sí se puedan preservar, que les ayude también a saber la composición o ciertas cosas que se quieren saber de ese patrimonio, artefacto. Entonces, pues es muy útil, ¿no? Y en otras cosas que a lo mejor no son como tanto de cuidado de patrimonio, pero que tienen que ver con cuestiones culturales, es que también está habiendo una cuestión de limpieza de superficies. En el caso, por ejemplo, de estatuas que tienen un recubrimiento de cierto metal, por ejemplo, de plata, pues con el tiempo se oxidan, entonces ya se ven como negras y ya no dan la apariencia que se quería. Lo que hacen muchos investigadores es ponerles sustancias químicas para limpiarlos, pero la desventaja es que se remueve mucho del material y muchas veces, como solo es una capa de recubrimiento, se pierde con el tiempo el recubrimiento. Lo que hace el LIBS es que puede hacer esa limpieza y como tiene pues una sensibilidad alta en cuanto a ver un cambio en el espectro, en que ya no es un óxido, sino ya se regresa a la plata, en ese tiempo inmediato se puede dejar de hacer la limpieza en ese sitio y se pasa a un sitio siguiente, ¿no? Entonces, de esa forma, se puede hacer una limpieza mejor y con menos pérdida del material. Y también ya son cuestiones que se están haciendo de análisis en patrimonio cultural con LIBS.
Okay. Pues, once again, thank you very much for this really interesting talk. I think it's got quite the potential for not just this archaeological or cultural application, but also I think in the characterization of new materials. We could use it, as you said, with other spectroscopic materials from on or FTIR, I guess. Now I will I will hand over to Dr. Del Rio. Thank you once again, Georgina.
Thank you.
Thank you, Farid. Thank you, Georgina. Thank you, Nicolas. I think that this is very illustrative example of the research that we are doing in National University of Mexico, and in particular in the Institute of Applied Technology. Thank you very much. And to the audience, thank you very much to be with us. And we will see you next time in this seminar of the Mexican Society of Students in United Kingdom support. Thank you very much, all of you.
Thanks.
Listo. Ya.